Hello, Math 2. This is Mrs. Bricky, and this video is for Unit 4, Lesson 2, which is on similarity. Last time we worked on dilations, and so you'll remember that if we have a dilated shape like A prime, B prime, C prime, this little green triangle, then there is a scale factor by which all of the lengths are multiplied from that original triangle ABC, and that if we connect the points, the corresponding points like A and A prime, we will have a center of dilation that we can find, which is labeled P in this diagram. So if a triangle or another shape is a dilation of a shape, then what we say in math is that the two shapes are similar. So last year you worked on congruence with shapes. So if you had two congruent shapes, it meant that they were exactly the same size and shape. This year we're working on similar shapes. So for triangle ABC, my blue triangle, it is similar to triangle A prime, B prime, C prime. We use this tilde, this squiggle right here, to denote similarity. But two similar shapes could also have experienced a rigid transformation, like a rotation or a reflection. So, for example, this pink triangle is also a dilation if we, move it into the right spot and rotate it. Oh, whoops. Oh, sorry. Sometimes goodness gracious, sometimes my tablet is harder to use than my smartboard. So you can see that the pink triangle is also can be thought of as a dilation. It just was rotated and sort of moved around. So triangle DEF is also similar to triangle ABC. These are called similarity statements, and the order that we put the points it matters. So I wouldn't want to say triangle FED. And the reason is that we want to keep the corresponding points in the same order. So point F is right here, so that corresponds to point C. So you can see that those letters both come last. And this one is point D. If I think about, having rotated and moved that around. So D is in the same location in the triangle name as the A. And then E would be this one, which is the middle letter on those similarity statements. So you want to make sure you get those similarity statements in the correct order. So if you were in class, we did an exploration where we measured some angles and things for the video. I'm going to skip past that. So here are the properties of similar figures that we discovered in class. For similar figures, they have the same shape, but not necessarily the same size. So I've got right here below triangle ABC is similar to triangle PQR. They have the same shape, but triangle PQR is a little bit smaller. The next property is that corresponding angles have equal measure, exactly the same angles. So in my diagram here, you can see that angle A, which is marked with that blue X, it's the same angle as angle P in my other triangle. Angle B and angle Q both have a degree measure of Y, and angle C and angle R both have a degree measure of Z. So corresponding angles have equal measure. And then finally, the corresponding sides are in the same ratio. So P divided by A is equal to Q divided by B, which is equal to R divided by C, and they are all equal in part because they are all, or one way of thinking about it is that those ratios are all equal to K, the scale factor. So we know that they are in the same ratio. Okay, so here's our first little example. I want to connect what we're doing today to what we did last time. we have two triangles, triangle A similar to triangle B. Last time we would solve for x using the scale factor, so I want to remind you how we did that. So to find the scale factor, we have to find a couple of corresponding sides. We've got this one that is a length of 9 and this one that is a length of 12. We want to put the new over the original, so 9 over 12, because we're thinking about it in this order. So our scale factor is 3/4. So that side length of 12 gets multiplied by 3/4 to give us 9. So to solve for x, we need to take that 8 and multiply it by that scale factor of 3/4. So x is equal to 8 multiplied by 3/4, which is 6. So that's how we would solve this problem last class as we were talking about dilations. It's when we start getting more into similarity, it's a lot more common to solve these types of problems using a proportion. A proportion is kind of a way of skipping the calculation of the scale factor. So, because I know that this fraction is equal to the scale factor, and I know that this fraction is equal to the scale factor, basically I can skip finding the scale factor and just set the two fractions equal to each other. So this is called setting up a proportion, and that's how we're going to solve in this next box. So I want to show you that method. So we identify corresponding sides still. So the side that I want to find is x, and the corresponding side in my other triangle is 8. So that's going to be my first fraction, x divided by 8. I like to put the thing I'm finding in the numerator, but there's definitely several ways you could set up this proportion. So I'm trying to figure out x, and x corresponds to 8. So my first fraction is x divided by 8. And then my other fraction will be another set of corresponding sides, in this case 9 divided by 12. So we now have an equation with an x in it, and we want to solve for x. Well, in this equation, x is being divided by 8, so we multiply both sides by 8. This one is canceled out, and we get that x is equal to 9/12 times 8, which is equal to 6, and you could use your calculator. And so, of course, we get the same answer just with two different methods. So you can probably see the parallels between the two. This idea is basically to just not calculate k directly, but just use proportion. And that's what we're going to do going forward in this lesson. So before we start looking at more shapes, I wanted to just practice solving some proportions. And we are going to solve for x on each of these. Now, on some of these, you might see another method for solving. I would like to emphasize that there are lots of different valid methods for solving proportions. I am going to solve them by thinking about it as division, but if you have another method that you've used in a past class or a trick that a teacher has taught you that you understand, you can definitely use that method. So in my first equation, I see that I have an x divided by 10. So I want to get that x by itself. So I'm going to multiply both sides of my equation by 10. This one cancels. So I'm left with x is equal to 9 divided by 6 times 10. So grab my calculator. That gives me 15. In my next equation, I have y minus 5 divided by 14 is equal to 3 halves. So I have a y minus 5 instead of just a y or just an x. But we want to actually just kind of treat that y minus 5 like it's our variable that we want to get by itself. Right now, the y minus 5 is divided by 14. So we want to multiply both sides of our equation by 14. That cancels out on the left. So on the left, I just have a y minus 5 now. I can use my calculator to calculate 3 divided by 2 times 14, and that is 21. So now to finish solving for y, I just need to add 5 to both sides of my equation. So I get y is equal to 26. My last equation over here is 4/9 is equal to x minus 3 divided by 6. So I want to get that x minus 3 by itself, so I'm going to multiply both sides of my equation by 6. On this one, I'm going to keep it in fraction form, but if you want to go into decimals, that's probably okay. So 6 times 4 divided by 9 is 8/3. The 6 on this side of the equation is reduced. So we have x minus 3. And so now to finish, I just need to add 3 to both sides of my equation. And 8/3 plus 3 is equal to 17/3. In decimal form, if you had gone to decimals, that's 5.67. That's a rounded answer. Okay, so what if the variable is on the bottom? Honestly, a lot of times when students see equations like this with the variable on the bottom, they panic or they feel like it's a lot harder. In reality, it's not a lot different. But one method that I think is pretty successful for a lot of students is the idea that if the variable is on the bottom, you can absolutely just flip the whole equation over. I'm not going to do that on number 6, but that's what I'm going to use on the other one. And sometimes students are like, why in the world does that work? Well, let me just write a couple of fractions that you know are true. We know that 4 divided by 8 is the same as 1/2. This is true. If I flip it over, it's 8 divided by 4 is equal to 2 divided by 1. It's still true. So you can just take an equation that has 2 fractions in it and just flip it over, and it's still another true equation. Okay, so if the x is in the denominator and it's making you feel like it looks difficult, you can just flip the whole thing over. So we have x over 7 is equal to 7 over 8. And now we can solve for x by multiplying both sides of our equation by 7. And we get, if we stay in fraction form, it's 49/8. If you go into decimals, that's 6.125. Okay, so we're going to use that same idea here. The x is in the denominator here on the right side, so we're going to just flip it over. So we have 2/5 is equal to 2x minus 1 all divided by 12. So to get that 2x minus 1 by itself, or just get us on our path to solving for x, we're going to multiply both sides of the equation by 12. This 12 cancels out. So now we have 24/5 is equal to 2x minus 1. And I'm going to go ahead and go into decimals for this one just for funsies. We've got 4.8 is equal to 2x minus 1. So we add 1 to get 5.8 is equal to 2x. And again, I just added 1 to both sides of my equation. And then finally, I just need to divide by 2. So that leaves me with that leaves us with 2.9 is equal to x. Okay, on this last equation, you might have noticed that it has 2 variables. So flipping this over isn't going to help us put the variable in the numerator. We just have 2 variables to deal with. We can use this idea of clearing the denominator, though. So on that first fraction, you notice that we have an x in the denominator. So what we're going to do is multiply both sides of our equation by x. On the left side, that x cancels out. So on our left side of our equation, we have x minus 3. I can put the x and the 9 sort of together in that numerator, so now I have x minus 3 is equal to 9x divided by 10. Well, I still have a fraction I would like to clear, so I'm going to now multiply both sides of my equation by 10. When I multiply the left side by 10, I have to remember that I have a binomial here, so I need to distribute that 10 when I multiply. So if we distribute the 10, we now have 10x minus 30 is equal to 9x. Now there's several ways you could get your final answer here. I'm going to go ahead and subtract the 10x. So I have negative 30 is equal to negative 1x or negative x, because 9 minus 10 is negative 1. And now you can think of it, if you want, like dividing by negative 1, or you can think of it like, adding the x and adding the 30, but we end up with that x is equal to 30. Okay, now that we've practiced solving proportions, we're going to go back to our similar shapes and see if we can solve for some different side lengths. So I've got triangle run, and it's similar to triangle pat. We were going to create a proportion that can help you solve for x, and then we're going to solve that proportion. So the side that I would like to find is this one right here, from A to P. And the side that that corresponds to in this other triangle is from R to U. Now, sometimes if you have a figure where the side lengths aren't a lot different, it can be difficult to tell which sides correspond. So you can always use your similarity statement to help you. You can see that P and A, which is the length I'm trying to find, are the first two letters in that triangle's name. And so I also need to use the first two letters here. It's R to U. So that you can use the similarity statement to help you match up corresponding sides if you're having a difficult time with that. So we have x divided by 5.8 for our first fraction, and we know that has to equal the ratio of two other corresponding sides. So the only other side in this triangle I have is this one, 4. Well, 4 connects the P and the T. That's the first and the last letter. So in my other triangle, I need the one that connects R and N. So that's this one right here. So, and you can, sometimes you can just tell. So maybe you looked at these two triangles and you were like, I can tell that the 4 corresponds to the 10. If that is the case, great. Just using the letters in the similarity statement is just a great strategy if you can't quite tell. So we started with the X on top and put it over the 5.8. So we're going to do the same for this set of corresponding sides. We're going to start with the 4 and put it over the 10. Okay, so now we have this equation, and we just need to do one thing to solve for x. We just need to multiply both sides of our equation by 5.8, and that gives us our answer. 4 divided by 10 times 5.8, which is 2.32. Okay, follow-up question. If the measure of angle N is 36 degrees, what other angle measure do you know? Well, remember that corresponding angles are congruent. So if angle N is 36 degrees, we also know that angle T has a measure of 36 degrees. All right, here we have some quadrilaterals. MNPQ is similar to RSTU. I'm going to not find Y for the video. I'm just going to focus on X and Z. So if I'm trying to find the side that is marked X, I have to think about what it corresponds to in my other shape, and it corresponds to ST. You can see that those are the middle letters in this quadrilateral. So my first fraction, I'm going to put the x on top and the 25 in the denominator. And I need to find another set of corresponding sides. And the only other one I know in this figure is SR. Well, SR corresponds to MN, so this is my other side I'm going to use. Because I put x over 25, I have to put for my second fraction 18 over 30. The 30 is in the denominator. So to solve for x, I just need to multiply both sides of my equation by 25. That cancels out, and we get, let's see, 18 times 25 divided by 30 is 15. So we know that x has a side length of 15. Okay, we are also going to find z. So z is this angle right here. Well, please, please, please try to remember that angles are, in similar figures, are congruent. Sometimes people will try to set up a proportion to find an angle, but angles are not scaled. Angles stay the same. Think about two little squares. They are similar to each other, but their angles are 90 degrees. Their angles do not change. So if we want to know the measure of angle z, we just have to look at that corresponding angle in the other quadrilateral. So z is equal to 115 degrees. Okay, in the triangles shown, they're similar to each other. It looks like we have a larger one and it got reflected over and then there's a smaller one. So we want to calculate the value of x. So what's happening is that we know that this taller triangle is extending 5 units above the shorter triangle. A lot of times in situations like this where the two figures are like connected to each other, it can be a great idea if you need to separate them into two different shapes. And that can kind of help you think about it a little bit. So we know that this side is 6 and we know that this side is x. Because the entire width of this weird shape is 10, we know that this length right here is 4. And then the maybe trickiest bit is to figure out the height of that taller triangle. Well, it's just broken into two pieces, an x and a 5. So that means that height is going to be x plus 5. Okay, so we're ready to set up a proportion here. I am going to start by putting the x plus 5 on top. You can do this proportion several ways, and they can all be correct. So just put the fraction, write down the first fraction that you kind of observe and see, and then think about another one that is sort of corresponding. So we've got an x plus 5, and that's going to be over an x. Those are the two heights of the triangles. And then we want to set up our other fraction. Well, I started with the numerator coming from the larger triangle, so I want my second numerator to also come from the larger triangle. So 6, and then that's going to be over 4. So to clear my denominator, I'm going to start by multiplying both sides of the equation by x. That one cancels out. So now I have an x plus 5 is equal to 6x over 4. I'm going to clear that 4 by timesing both sides of my equation by 4. This one cancels. On this side, we have to remember to distribute. So that gives us 4x plus 20 is equal to 6x. And we're going to wrap this up by subtracting the 4x. So we now have 20 is equal to 2x, which means that x is equal to 10. So that gave us our value for x, and that kind of makes a lot of sense if you look at the diagram. I mean, I guess you can't always assume that a diagram is to scale, but if this x is 10, that means the height of this larger triangle is 15, and the smaller triangle has a height of 10, and that does kind of make sense based on the diagram. Okay, this is the last example for the video. Are the statements listed below true or false? If it's true, try to kind of explain why you know it's true, and if it's not true, try to give a counter example. So think about an equilateral triangle. Are all of the equilateral triangles similar? Well, they definitely all have the same angles. So now we would just have to think about, are their sides in the same proportion? And I think hopefully you can see that that would be true because whatever this side gets multiplied by, this one would also get multiplied by. Since all three sides are the same, we can definitely find a scale factor to connect those two shapes. So this is true. All equilateral triangles are similar. The next one is about rectangles. So maybe think for a second if you think all rectangles are similar, and if you can kind of explain why, or if you can provide a counter example. Here's a good counter example. Those are both rectangles, but they are definitely not similar. Same situation with right triangles. They can be similar, but they definitely are not all similar. I could have one that has sort of different proportions, and they would not be similar. But circles, if you think about circles, they are all similar. So not true that rectangles are similar, not true that all right triangles are similar, but yes, it's true that circles are similar.